What if I told you that everything we see, every star, every galaxy, even the light from your screen now makes up less than 5% of the universe? The rest, a cosmic mystery hiding in plain sight. Scientists call it the universe's missing energy, dark energy, and dark matter, invisible forces shaping the cosmos in ways we're only beginning to grasp. Think about that for a moment. The vast expanse of space, filled with billions of galaxies, is just the tip of an iceberg we can't fully see or touch. It's like staring at a grand puzzle where most of the pieces are missing, and the ones we have don't quite fit together. This isn't just a small gap in our understanding, it's a chasm. For decades, the brightest minds in physics have wrestled with this enigma, proposing wild, brilliant, and sometimes contradictory theories to explain where this missing energy comes from and what it means for the fate of everything. Some say dark energy is stretching the universe apart faster than we ever imagined. Others suggest hidden dimensions or undiscovered particles might hold the key. And then there are the theories so strange they sound like science fiction, parallel universes leaking energy into ours, or even flaws in the very fabric of reality itself. That's what makes this mystery so thrilling. It's not just about filling in a blank spot on a cosmic map. It's about rewriting the rules of physics, challenging everything we thought we knew. And today, we're diving headfirst into 30 of the most fascinating theories, from the cutting edge of science to the edges of imagination. By the end, you might not have all the answers, but you'll see the universe in a whole new light. So buckle up, we're about to take a journey into the unknown, where every theory is a step closer to unraveling the greatest secret the cosmos has ever kept. Let's start with something mind-bending, the idea that empty space isn't actually empty. Even in the deepest voids between galaxies, where it seems like nothing exists, quantum mechanics tells us there's a hidden frenzy of activity. Tiny particles and antiparticles flicker into existence and vanish almost instantly, like bubbles forming and popping in a cosmic foam. These are called quantum vacuum fluctuations, and they might hold the key to dark energy. Think of space itself as an invisible ocean, with waves constantly rising and falling at the smallest scales imaginable. These fleeting particles borrow energy from the universe for mere fractions of a second before disappearing again. But here's the twist. According to Einstein's theory of relativity, energy and mass are two sides of the same coin. That means even this fleeting activity could add up to a massive, invisible force pushing the universe apart. The problem, measuring it. These particles exist on such unimaginably tiny scales and timespans that they're nearly impossible to detect directly. And when scientists try to calculate how much energy these fluctuations might contribute to dark energy, the numbers are catastrophically wrong, off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, a discrepancy so enormous it's been called the worst theoretical prediction in the history of physics. Yet the idea persists because it's so elegant. If we could somehow reconcile the math, quantum vacuum fluctuations might explain why the universe isn't just expanding but accelerating. Some theorists suggest we're missing a crucial piece of the puzzle, maybe undiscovered particles or even flaws in our understanding of gravity itself. Others wonder if these tiny fluctuations could be leaking energy from other dimensions, a cosmic bleed over from realms we can't yet perceive. It's a theory that straddles the line between solid science and wild speculation, but that's what makes it so compelling. If true, it would mean the very fabric of nothingness is driving the fate of everything, and that's just the first piece of this cosmic puzzle. Wait until you hear what's next. Einstein might have called it his greatest blunder, but sometimes even geniuses underestimate their own ideas. When he first proposed the cosmological constant in 1917, it was meant to balance the equations of general relativity, a mathematical fudge factor to keep the universe static, because like most scientists of his time, Einstein assumed the cosmos was unchanging. But when Edwin Hubble discovered the universe was actually expanding, Einstein tossed the idea aside, dismissing it as unnecessary. Decades later, that so-called blunder made a shocking comeback. In the late 1990s, astronomers observing distant supernova made an earth-shattering discovery. Not only was the universe expanding, but that expansion was speeding up. Something was pushing galaxies apart faster and faster against the pull of gravity. Suddenly, Einstein's discarded cosmological constant didn't look so foolish after all. In fact, it became the leading explanation for dark energy, a fixed, invisible energy woven into space itself, stretching the fabric of reality a little more every second. Here's how it works. Imagine space as a stretchy rubber sheet. The cosmological constant would be like tiny springs embedded in that sheet, constantly pushing outward. Unlike matter or radiation, whose influence fades as the universe grows, this energy density stays constant, meaning its effects become more dominant as space expands. It's a beautifully simple solution, requiring no new particles or dimensions, just a slight tweak to Einstein's original equations. But simplicity doesn't always mean correctness. The cosmological constant comes with its own massive puzzle, the vacuum catastrophe. When physicists calculate how much energy empty space should contain based on quantum theory, the number is astronomically larger than what we observe. We're talking about a discrepancy of 1 with 120 zeros after it. That's like predicting a cup of coffee should boil the entire ocean, only to find it's barely warm. This glaring mismatch keeps many scientists skeptical. Some argue the cosmological constant is just a placeholder for something far stranger, a sign that our understanding of quantum mechanics and gravity is incomplete. Others propose that multiple competing effects in the quantum foam might cancel each other out in ways we don't yet grasp. And then there's the unsettling coincidence that the constant's value happens to be just right for life to exist, a puzzle known as the fine-tuning problem. What makes this theory so fascinating is its duality. On one hand, it's the simplest, most elegant fix to our equations. On the other, it raises questions so profound they might require a revolution in physics to answer. Einstein's blunder could still be the key to the universe's fate, or it might be a clue pointing to something even more extraordinary waiting to be discovered. What if dark energy isn't constant at all? What if it's something fluid, changing, almost alive in the way it shapes the cosmos? That's where quintessence comes in, a theory so poetic it borrows its name from the ancient Greek idea of a fifth element beyond earth, air, fire, and water. But this isn't philosophy. It's a radical reimagining of dark energy as a dynamic force, one that ebbs and flows across the lifespan of the universe. Unlike the rigid cosmological constant, quintessence suggests dark energy could vary over time and space. Picture it like a cosmic weather system, sometimes a gentle breeze nudging galaxies apart, other times a gale force accelerating expansion in fits and starts. This flexibility solves some of the stickiest problems with the cosmological constant, like the fine-tuning mystery. Instead of requiring inexplicably perfect conditions from the start, quintessence allows dark energy to evolve naturally, adjusting its influence as the universe grows. The math behind it is mesmerizing. Quintessence is often modeled as a hypothetical energy field, with properties resembling an exotic, ultra-light particle. Imagine a ghostly mist permeating all of space, its density shifting as the universe ages. Early on, when matter was densely packed, this field might have lain dormant, overshadowed by gravity's pull. But as galaxies drifted farther apart, quintessence could have awakened, its repulsive force gradually dominating the cosmos. Here's where it gets even stranger. Some models suggest quintessence isn't just changing, it could be decaying. If true, the accelerating expansion we see today might someday reverse, like a stretched rubber band snapping back. That opens the door to wild possibilities, a big crunch where the universe collapses in on itself, or cyclical universes rising and falling in an endless dance. But Quintessence isn't without its critics. For one, we've never detected a particle or field that behaves this way. It's also fiendishly difficult to test. Unlike the cosmological constant, which makes clear predictions, Quintessence comes in countless flavors, each with slightly different rules. It's like trying to identify a spice in a stew when the recipe keeps changing. Yet the theory's allure is undeniable. It turns dark energy from a static oddity into a living, breathing player in cosmic history, one that might still surprise us. And if Quintessence is real, it wouldn't just solve a puzzle. It would rewrite the story of the universe, casting its fate as something still unfolding, still uncertain. That's a twist even Einstein might not have seen coming. What if the problem isn't missing energy, but missing gravity? That's the radical proposition of modified Newtonian dynamics, or MOND, a theory that dares to rewrite the rules we've relied on since Newton watched an apple fall. Instead of invoking invisible dark energy to explain the universe's acceleration, MOND suggests we've simply misunderstood how gravity works on cosmic scales. It's like realizing you've been reading the map upside down and the destination was never where you thought. At its core, MOND tweaks Newton's second law of motion, which says force equals mass times acceleration. For centuries, this equation held true until astronomers noticed galaxies rotating way faster than they should based on visible matter alone. Instead of adding dark matter to balance the books, MOND proposes that gravity behaves differently when acceleration becomes incredibly weak, like the faint tug between distant stars. Modify the math just slightly and suddenly, galaxies behave as observed, no invisible stuff required. The implications are staggering. If MOND is correct, Einstein's general relativity, the gold standard of cosmic physics, might need adjustments in low acceleration environments. Picture relativity as a flawless Swiss watch that keeps perfect time on Earth but ticks oddly in deep space. Proponents argue this could erase the need for dark energy entirely, framing cosmic acceleration as a quirk of gravity's hidden rules rather than an unknown force. Yet MOND faces fierce resistance. For one, it struggles to explain all observations like the Bullet Cluster, where colliding galaxies show gravitational effects separate from visible matter, seemingly proving dark matter's existence. Critics also point out that MOND lacks the elegance of a deeper underlying principle. It's more of a mathematical patch than a unified theory. And then there's the cultural hurdle. Challenging Einstein is the scientific equivalent of rewriting the Constitution. But here's why it matters. MOND forces us to question assumptions we've held for centuries. Maybe dark energy is like the mythical ether physicists once believed filled space, a placeholder for something we just haven't grasped yet. Or maybe gravity is whispering secrets we've been too stubborn to hear. Either way, MOND reminds us that the universe's greatest mysteries might not lie in what we've failed to find, but in what we've failed to question. Imagine a force so relentless, so voracious, that it doesn't just expand the universe, it devours it. Phantom energy takes the idea of dark energy and cranks it to a nightmarish extreme. Unlike the cosmological constant or even Quintessence, this isn't just about gentle acceleration. Phantom energy could grow stronger over time, its grip on space-time tightening until the fabric of reality itself shatters in a catastrophe cosmologists call the Big Rip. Picture this: billions of years from now, the expansion of the universe doesn't just pull galaxies apart, it escalates. First, galaxy clusters are ripped from one another. Then, individual galaxies are torn asunder. Stars, planets, even atoms are wrenched apart as the phantom energy's repulsive force overwhelms every fundamental force in nature. In the final moments, space-time itself is shredded, leaving behind a cold, empty void where the universe once was. It's not just an end, it's annihilation on a scale so absolute it defies comprehension. The math behind phantom energy is as unsettling as its implications. Most dark energy models assume its density remains constant or fades over time, but phantom energy, its density increases. It's like blowing up a balloon that never stops inflating, stretching thinner and thinner until it pops. The kicker: observations of distant supernova and cosmic microwave background radiation don't entirely rule this out. Our current data could, in theory, allow for phantom energy's existence, though just barely. Yet there's a catch. If phantom energy were real, we'd expect to see certain telltale signs, like galaxies being pulled apart faster than standard dark energy predicts. So far, the evidence isn't conclusive. Some researchers argue that phantom energy's extreme behavior would have already left obvious scars on the cosmos, while others counter that its effects might still be subtle, lurking just beyond our current observational limits. What makes this theory so gripping isn't just its apocalyptic finale, it's the questions it forces us to confront. If phantom energy exists, how close are we to that tipping point? Could it explain why dark energy's effects seem so finely tuned for life now? Or is it a cosmic red herring, a reminder that the universe's fate might be stranger than anything we've dared to imagine? One thing's certain: in the hunt for the universe's missing energy, phantom energy is the wild card, a theory as terrifying as it is electrifying. There's a theory so audacious it dares to solve two cosmic mysteries with one stroke: an exotic substance known as Chaplygin gas. Imagine a fluid that starts its life behaving like dark matter, clumping together under gravity's pull to sculpt galaxies, then transforms into something eerily like dark energy, driving the universe apart with relentless force. This isn't science fiction. It's a mathematical sleight of hand that could rewrite our understanding of the cosmos's missing ingredients. The beauty of Chaplygin gas lies in its simplicity. At its core, it's a perfect fluid with a pressure that decreases as its density grows, a bizarre property that defies everyday intuition. Think of it like honey that thickens the more you stir it, except here, the honey is a cosmic medium filling the voids between galaxies. Early in the universe's history, when matter was densely packed, this fluid would have acted like cold, dark matter, gravitationally attracting itself to form the seeds of galaxies. But as expansion stretched space thin, the gas's strange physics would kick in, morphing it into a repulsive force eerily similar to dark energy. One substance, two roles, a cosmic shape-shifter hiding in plain sight. Mathematically, it's a masterpiece of elegance. The equation describing Chaplygin gas fits snugly into general relativity, requiring no new particles or dimensions. It's like finding a single key that unlocks two separate doors. Proponents argue this could resolve the awkward coexistence of dark matter and dark energy in our models, two enigmatic entities that, until now, seemed entirely unrelated. But elegance doesn't always equal truth. Critics point to glaring gaps. For one, Chaplygin gas struggles to explain the intricate dance of galaxy clusters, where dark matter's gravitational fingerprints don't quite match the fluid's predicted behavior. There's also the issue of sound waves in the early universe, cosmic ripples recorded in the microwave background that seem to contradict how this exotic medium should propagate. And then there's the philosophical objection: is it too convenient? A universe where two profound mysteries neatly collapse into one feels almost engineered. Yet the theory persists, fueled by its tantalizing promise. Maybe Chaplygin gas isn't the final answer, but a stepping stone to something deeper, a hint that dark matter and dark energy are threads of the same unfathomable fabric. Or perhaps it's a red herring, a dead end in the labyrinth of cosmic enigmas. Either way, it forces us to ask a haunting question. What if the universe's greatest secrets aren't hidden in the darkness, but in the spaces between what we've already imagined? What if the three-dimensional universe we experience is just an illusion, a cosmic mirage projected from a two-dimensional surface at the edge of reality? This isn't a plot from a sci-fi movie. It's the holographic principle, a theory so revolutionary it could redefine where the universe's missing energy is hiding. Imagine the cosmos as a giant movie screen with everything we see. Stars, planets, even our own bodies being nothing more than shadows cast by information encoded on a distant, flat boundary. At the heart of this idea lies a startling revelation from black hole physics. When matter falls into a black hole, its information isn't lost. Instead, it's smeared across the event horizon like ink on a piece of paper. Physicists realized this two-dimensional surface could hold all the data needed to reconstruct the three-dimensional world inside. Extend this logic to the entire universe, and you get the holographic principle. Every bit of energy, every particle, every force we perceive might just be pixels in a vast cosmic projection. So how does this solve the dark energy puzzle? The answer lies in information density. In a holographic universe, there's a fundamental limit to how much data can be packed into a given space. It's like trying to fit an entire library onto a single flash drive. Eventually, you hit a wall. This constraint could naturally cap the energy density of the vacuum, preventing the catastrophic numbers predicted by quantum field theory and aligning with the faint, smooth, dark energy we observe. Instead of an inexplicable fine-tuning, the holographic principle suggests dark energy is simply the universe running out of storage space, but the implications go deeper. If the holographic principle is correct, it would mean the fabric of reality is fundamentally pixelated with a smallest possible unit of space and time. This could explain why dark energy's effects are so subtle. It's not a force in the traditional sense, but a side effect of how information is rendered at cosmic scales. Think of it like a video game struggling to render too many details at once. The universe might be lagging under its own computational limits. Critics argue the theory is still speculative, lacking direct experimental proof. Yet tantalizing clues exist. Some models suggest the holographic principle could leave fingerprints in the cosmic microwave background, subtle imprints of a pixelated universe. Others propose that gravitational wave detectors might one day catch whispers of this two-dimensional code vibrating through spacetime. Whether the holographic principle holds the key to dark energy or not, it forces us to confront a profound possibility. The universe might not just contain information. It might be information, a cosmic masterpiece painted on the thinnest canvas imaginable. And if that's true, the missing energy isn't lost. It's just written in a language we're only beginning to decode. Picture our universe not as an island in empty space, but as a sheet of paper floating in a vast, unseen ocean, an ocean with dimensions beyond the three we know. This is the essence of brane cosmology, a theory that reimagines reality itself. The word brane comes from membrane, and in this model, our entire cosmos could be one such surface adrift in a higher dimensional realm called the bulk. But here's where it gets wild. Other brane's parallel universes might be drifting nearby, invisible to us yet close enough to leave fingerprints on our reality. How could this explain dark energy? Imagine two branes normally separated by an invisible gap, slowly drawn together by gravity. If they collide or even graze each other, the energy released could flood our universe like water bursting through a dam. Some theorists suggest this is the source of the cosmic acceleration we observe, not a mysterious force from within, but a shock wave from a hidden dimension. It's as if the universe is being pushed by something we can't see, like a ship rocked by waves from an unseen storm. One version of this idea, the ekpyrotic model, proposes that our Big Bang wasn't the beginning of everything, just the moment our brane slammed into another, igniting a firestorm of energy that became galaxies, stars, and us. Instead of a singular explosion from nothing, the universe cycles through brane collisions, each resetting the cosmic clock. Dark energy, then, might be the lingering ripple of that ancient impact, or even the slow build-up to the next one. But brane cosmology isn't just about brute force collisions. Subtler interactions could be at play. higher dimensional gravity, the true, unfiltered force might leak into our brain, manifesting as the repulsive push we call dark energy. Think of it like a shadow puppet. The real movement happens in a dimension we can't access, while we only see the distorted effect. Critics argue the theory is hard to test. How do you detect a dimension folded smaller than an atom, or a parallel brane that might be millimeters away yet entirely unreachable? Yet there's hope. If extra dimensions exist, particle colliders might one day produce debris that vanishes into them, like marbles rolling off a table into thin air. Gravitational waves could carry echoes of brane vibrations, hints of a larger reality just out of view. Brane cosmology forces us to confront a humbling possibility. What we call dark energy might not belong to our universe at all. It could be the cosmic equivalent of a neighbor's music bleeding through the walls, a reminder that we're not alone but part of something impossibly bigger. And if that's true, the missing energy isn't lost, it's just waiting next door. What if the speed of light, the cosmic speed limit etched into physics textbooks, wasn't always the same? It's a heretical thought, challenging one of Einstein's foundational principles. But a handful of physicists dare to ask, could light have raced faster in the early universe, and could that explain dark energy's grip on the cosmos without inventing new forces or particles? At first glance, the idea seems impossible. Einstein's relativity hinges on light's speed being constant, a fixed yardstick against which all motion is measured. But peel back the layers and cracks emerge. When we peer at distant galaxies, their light stretched redder than expected. We assume it's because space itself is expanding. But what if that redshift isn't from expansion at all? What if it's because light slowed down over cosmic time, like a runner losing stamina mid-race? Proponents of variable speed of light, or VSL, argue this could elegantly mimic dark energy's effects. If light moved faster in the past, ancient supernova would appear fainter than predicted, exactly what astronomers observe when they measure cosmic acceleration. No mysterious repulsive force needed, just a subtle rewrite of how light behaves across eons. It's like realizing your car's speedometer was mislabeled all along. The road wasn't bending, your measurements were off. The math reveals startling possibilities. In some VSL models, the shift in light speed could be tied to the universe's temperature. Picture the early cosmos as a searing plasma where photons darted freely, unimpeded. As space cooled, light might have stiffened, slowing as spacetime itself crystallized into today's familiar fabric. This could neatly explain why dark energy's influence seems so recent in cosmic terms. It's not an emerging force, but a fading echo of light's primordial sprint. Critics pounce on glaring weaknesses. For one, altering light's speed unravels relativity's tapestry, potentially invalidating everything from GPS satellites to nuclear power. There's also no direct evidence, just tantalizing what-ifs. Yet VSL lingers because it dares to question dogma. After all, constants like the gravitational fine structure parameter might not be so constant either. If other fixed values shift over time, why not light speed? The theory's real power lies in its audacity. It forces us to confront an unsettling truth. Our cosmic models are built on assumptions we've rarely tested across billions of years. Dark energy might not be missing, just misunderstood, hidden in plain sight within the rules we thought we knew by heart. And if that's true, the universe's greatest secret might not be in the darkness ahead, but in the light behind us. Gravity might not be a fundamental force at all, but a side effect of cosmic chaos. That's the radical premise of entropic gravity, a theory where the invisible glue holding galaxies together emerges not from warped spacetime, but from something far stranger: entropy, the universe's tendency toward disorder. Imagine gravity as the universe's way of keeping its books balanced, a cosmic accountant ensuring energy gets distributed fairly. This isn't just a poetic metaphor. It's a mathematical revolution that could explain dark energy in one breathtaking swoop. The idea hinges on a startling connection between gravity and thermodynamics, the science of heat and energy flow. In the 1970s, physicist Jacob Bekenstein discovered that black holes have entropy, a measure of their hidden information. Later, Stephen Hawking proved they also radiate heat, linking gravity to thermodynamics irrevocably. Fast forward to 2010, when physicist Eric Verland took this further, proposing that gravity itself might be an emergent phenomenon, bubbling up from the statistical dance of microscopic degrees of freedom in spacetime. Think of it like temperature. We feel it as heat, but it's really the average motion of countless molecules. Similarly, gravity could be the macroscopic effect of microscopic information shuffling. Here's where dark energy enters the picture. If gravity emerges from entropy, then the accelerating expansion of the universe might just be the cosmos maximizing its disorder, a thermodynamic inevitability. Picture a box of gas. It naturally expands to fill its container, spreading out to achieve equilibrium. Now scale that up to the universe. As space stretches, the entropy associated with its horizon increases, creating an apparent force that drives galaxies apart. No mysterious dark energy required, just the universe doing what it's always done, seeking balance. But entropic gravity isn't without its skeptics. For one, it struggles to explain precise orbital motions of stars in galaxies without invoking some form of dark matter. Critics also argue it's more of a reinterpretation than a full-fledged theory, lacking predictive power where general relativity shines, like with gravitational waves. Yet its elegance is undeniable. By framing gravity as an information-driven effect, it bridges quantum mechanics and general relativity in a way no other approach has, hinting that the universe's missing energy might not be missing at all, just miscounted. What makes this theory so compelling is its audacious simplicity. It suggests we've been staring at the cosmic ledger all wrong. Dark energy could be less about an unknown force and more about the universe's bookkeeping and emergent tax imposed by the laws of thermodynamics themselves. And if that's true, the greatest mystery in cosmology might boil down to a single profound truth. Gravity isn't pulling the strings, information is. What if dark energy isn't a fixed cosmic dial, but a knob that's been turning all along? Time-varying dark energy flips the script on everything we thought we knew, suggesting the force accelerating our universe may have been stronger or weaker in different cosmic eras. Recent observations are stirring the pot. Quasars billions of light-years away show absorption patterns that don't quite match expectations if dark energy were constant. It's as if we're reading pages from a cosmic diary where the rules change from chapter to chapter. Think of dark energy like a tap controlling the universe's expansion rate. In the standard model, that tap is frozen in place, always letting through the same amount of push. But time-varying models propose the tap could have been wide open during the universe's adolescence, then tightened as galaxies matured. Or perhaps it dripped weakly at first, only surging to full strength in recent epochs. These fluctuations would leave subtle fingerprints, ancient supernova appearing brighter or dimmer than they should, or gravitational lensing patterns that warp space in unexpected ways. One tantalizing clue comes from the Lyman alpha forest, a peculiar pattern of absorption lines in quasar light caused by ancient hydrogen clouds. These cosmic barcodes suggest dark energy's influence might have dipped around 9 billion years ago, like a cosmic lung taking a deep breath before exhaling into today's accelerated expansion. Another hint lies in the clustering of galaxies. If dark energy's strength truly oscillates, vast galaxy surveys should reveal voids and filaments sculpted by these shifting tides. The implications are staggering. A varying dark energy could mean the universe's fate isn't sealed. Instead of an inevitable cold, empty expansion, we might face cycles of acceleration and deceleration, or even a future where dark energy fades entirely, allowing gravity to regain control. Some models suggest dark energy could be entangled with dark matter, the two locked in a dance where one's dominance fuels the other's retreat. Others propose it's tied to hypothetical particles that decay or transform over cosmic time, like radioactive elements with half-lives measured in eons rather than seconds. Critics argue these variations could just be measurement errors or gaps in our understanding of ordinary astrophysics. But if the hints hold up, we're looking at a universe far more dynamic than we imagined. One where the very fabric of reality tunes its own expansion like a musician adjusting tempo mid-song. That would rewrite not just cosmology's future, but its past. The Big Bang might have been one act in an endless cosmic drama, with dark energy as its ever-changing director. Deep in the equations of particle physics lies a symmetry so perfect it could rewrite the rules of reality: supersymmetry. This elegant theory, often called SUSY, proposes that every known particle in the universe has a hidden twin, a superpartner lurking just beyond our detection. For decades, scientists have chased these shadow particles, convinced they could solve everything from the hierarchy problem to the nature of dark matter. But there's another tantalizing possibility. What if these elusive superpartners are also the architects of dark energy, their ghostly decays silently fueling the universe's accelerating expansion? Here's how it could work. In a SUSY universe, particles we know like electrons and quarks would be paired with heavier, undiscovered twins. Photons would have photinos, gravitons would have gravitinos, and so on. These superpartners aren't just theoretical window dressing. Their existence would stabilize the quantum vacuum, preventing the explosive energy fluctuations that otherwise make dark energy's observed value so bafflingly small. But the real magic happens when these particles decay. Some SUSY models suggest certain superpartners could disintegrate into lighter particles, releasing energy that subtly tweaks the fabric of spacetime itself, like invisible hands stretching the cosmic canvas from within. The numbers tell a compelling story. If superpartners exist, their masses would naturally align with the energy scale needed to explain dark energy's faint but pervasive influence. It's as if the universe left breadcrumbs in the math. The same equations that demand SUSY existence also hint at a hidden energy source perfectly balanced to drive cosmic acceleration. Even more intriguing, some versions of SUSY predict our parity violation, where superpartners don't just decay, they transform, leaking energy into dimensions we can't perceive. This could manifest as a constant, uniform push on the universe, mimicking the cosmological constant but with a particle physics pedigree. Yet SUSY's biggest hurdle is the silence of our detectors. Despite years of searching at the Large Hadron Collider and other experiments, superpartners remain stubbornly absent. Critics argue this absence undermines the theory, pushing proposed particle masses into ranges that seem unnatural. But SUSY enthusiasts counter that we might be looking for the wrong signals. If superpartners are just slightly heavier than expected, or decay in unconventional ways, their fingerprints could be hiding in plain sight, woven into the cosmic microwave background or etched in the distribution of galaxies. What makes SUSY so captivating isn't just its explanatory power, but its audacious vision of cosmic balance. It suggests a universe where every force, every particle has a mirror, a symmetry so profound it could unite gravity with quantum mechanics while quietly powering the expansion of everything. The irony is delicious. The very particles we invented to solve one mystery might be the key to another. Their invisible dance writing the fate of the cosmos in mathematics we're only beginning to decipher. What if the mystery of our universe's missing energy has nothing to do with our universe at all? Imagine an infinite array of parallel realities, some nearly identical to ours, others wildly different, each with its own physics, its own history. Now picture energy silently slipping between them like water seeping through cracks in a dam. This is the multiverse's energy leak, a theory that dares to ask, could dark energy be nothing more than the cosmic toll for existing in a neighborhood of universes? The mechanics are as fascinating as they are speculative. quantum tunneling, a well-established phenomenon where particles teleport through seemingly impenetrable barriers, could provide the escape route. In labs, we've seen electrons vanish from one side of an obstacle and reappear on the other, as if borrowing energy from the future. Scale this up to cosmic proportions, and entire swaths of our universe's energy might be tunneling into adjacent realities, leaving behind the faint deficit we call dark energy. It's like living in an apartment where the heat keeps vanishing into the walls, except the walls are other dimensions. Black holes offer another eerie possibility. Some models suggest these gravitational monsters might not be dead ends for matter, but portals. The information paradox, the puzzle of what happens to data swallowed by a black hole, could find its answer if that information isn't destroyed but funneled elsewhere. Energy escaping through these cosmic drains might explain why the universe's expansion accelerates, not because of a mysterious push from within, but because of a subtle pull from without. But is any of this plausible? The math is tantalizing but treacherous. Quantum tunneling between universes would require unimaginably rare conditions, like a cosmic-scale Einstein-Rosen bridge woven from the fabric of spacetime itself. And black hole energy loss, we'd need evidence that singularities don't just crunch matter, but redistribute it across realities. So far, no detector has caught even a whisper of energy bleeding into another dimension. Yet the idea lingers because it solves two puzzles at once. If energy can leak out, other universes might be leaking energy in, balancing the cosmic books. This could explain why dark energy's density is so perplexingly small. It's not finely tuned, but averaged across countless realities. And it offers a spine-tingling vision of cosmology, our universe not as a solitary island, but as one leaf in a swirling multiversal storm, forever exchanging breath with worlds we'll never see. Critics call it a cop-out, a fancy way of saying the answer's somewhere else. But proponents argue it's no different from early astronomers realizing Earth wasn't the center of the solar system. Sometimes the truth isn't hidden in the details of what we see, but in the vastness of what we don't. Whether this theory holds water or energy remains to be seen. But one thing's certain, if the multiverse is stealing our energy, it's the greatest heist in history, and we're just beginning to notice the vault is empty. Dark matter has always played the role of the universe's silent architect, an invisible scaffold shaping galaxies with its gravitational pull. But what if it's not as stable as we think? Imagine dark matter particles, those elusive building blocks of the cosmos, slowly disintegrating over billions of years, their decay releasing bursts of energy into the void. This isn't just a cosmic slow burn, it could be the hidden engine behind dark energy's relentless push. The math behind this idea is as elegant as it is revolutionary. If certain dark matter particles are unstable, their gradual breakdown would inject energy into space itself, subtly altering the universe's expansion rate. Picture a campfire dwindling to embers, except instead of heat, the fading particles emit a repulsive force that counteracts gravity's pull. Over time, as more dark matter decays, this effect would accumulate, accelerating the separation of galaxies like an invisible hand pressing down on cosmic fast-forward. Some models suggest specific candidates for this decaying dark matter, like sterile neutrinos or hypothetical weakly interacting massive particles, or WIMP, with just the right properties to unravel at a glacial pace. These wouldn't vanish all at once, they'd fade in a way that perfectly matches the observed acceleration, like a clockwork mechanism ticking in sync with the cosmos. Other theories propose even stranger possibilities, like dark matter particles transforming into lighter, energy-rich daughters that interact even less with ordinary matter, leaving behind only their gravitational fingerprint as they disperse. But here's where it gets really interesting. If dark matter decay is real, it could solve two puzzles at once. First, it would explain why dark energy's influence seems so recent in cosmic terms. because the decay process would only dominate after the universe expanded enough for dark matter to thin out, reducing its gravitational dominance. Second, it might account for discrepancies in galaxy cluster behavior, where certain structures appear missing some of their expected dark matter. Perhaps that missing mass didn't vanish, it simply dissolved into the energy now stretching space-time apart. Critics point to glaring challenges, though. For one, we've never directly detected dark matter, let alone observed it decaying. The theory also requires exquisitely fine-tuned decay rates. Too fast, and the universe would have torn apart long before galaxies formed. Too slow, and the effect would be negligible today. And then there's the cosmic microwave background, whose precise temperature patterns currently align better with stable dark matter models. Yet the idea lingers because of its sheer audacity. It turns dark matter from a passive spectator into an active player in cosmic evolution, its slow unraveling scripting the fate of everything. If true, it would mean the universe's expansion isn't driven by some mysterious new force, but by the quiet, inevitable fading of its oldest and most enigmatic substance. The very shadows holding galaxies together might also be the reason they're drifting apart. A cosmic irony so profound it could rewrite our understanding of reality itself. Einstein's general relativity gave us a universe where gravity is the curvature of spacetime, a smooth, geometric dance where matter tells spacetime how to bend and spacetime tells matter how to move. But what if that dance has a hidden twist literally? The Einstein-Cartan theory proposes that spacetime isn't just warped, it's twisted like a spiral staircase hidden within the fabric of reality. This subtle but profound modification could rewrite our understanding of dark energy, turning it from a mysterious force into an inevitable consequence of spacetime's forgotten geometry. At the heart of this idea lies torsion, a property of spacetime that accounts not just for curvature but for rotation. Picture a bowling ball on a trampoline. In general relativity, its weight creates a smooth dip. But in Einstein-Cartan's universe, the ball's spin would also twist the fabric, adding a corkscrew-like distortion. These twists, long ignored in mainstream physics, might be the missing link to dark energy's repulsive push. Here's how it works on cosmic scales. As the universe expands, matter thins out but spin doesn't. Every electron, quark, and black hole pirouetting through space contributes to torsion's cumulative effect. Over billions of years, these microscopic twists could add up to a macroscopic force, gently counteracting gravity's pull. It's like a vast cosmic spring, coiled tighter as the universe grows, eventually releasing its tension by pushing galaxies apart. The math reveals something even more startling. In Einstein-Cartan's framework, torsion naturally produces a repulsive term in the equations, one that looks exactly like the cosmological constant, but with a clear physical origin. No mysterious energy field needed, just the intrinsic spin of matter itself, woven into spacetime's structure. This could solve the vacuum catastrophe too, since torsion's effects don't rely on quantum vacuum fluctuations and their infamous energy mismatches. Critics argue that torsion's influence should be negligible, as particle spins ordinarily cancel each other out. But proponents counter that cosmic voids, the vast, empty regions between galaxies, might let torsion dominate. With no matter to balance the spins, these voids could become reservoirs of twisted spacetime, their accumulated energy driving acceleration. Others suggest black holes, with their extreme rotational energies, might act as torsion amplifiers, seeding dark energy's growth like invisible power plants. Observational tests are scarce but tantalizing. If torsion is real, spinning neutron stars might warp spacetime differently than predicted by relativity alone, subtly altering their gravitational waves. The universe's large-scale structure could also bear torsion's fingerprints, with galaxy clusters aligning in unexpected ways. And then there's the profound philosophical shift. If Einstein-Cartan is right, dark energy isn't an added ingredient. It's baked into the universe's geometry from the start, a natural echo of everything that spins. What makes this theory so compelling is its audacious simplicity. It doesn't invent new particles or dimensions, it just asks us to look deeper at the equations we already have. Sometimes the universe's greatest secrets aren't hidden in the unknown, but in the details we've overlooked. And if space-time truly has a twist, it might finally unravel the mystery of why everything is flying apart. What if our entire universe is just the interior of a black hole? Not the crushing singularity we imagine, but the vast, structured expanse inside an incomprehensibly massive higher dimensional object. This isn't science fiction, it's a serious theory that could explain dark energy as a side effect of our cosmic confinement. Picture a black hole not as a pit of destruction, but as a cosmic Russian nesting doll, with our universe encoded on its boundary like a holographic sticker. The math behind this idea is as elegant as it is strange. When matter falls into a black hole, its information isn't lost, it's smeared across the event horizon, the point of no return. This holographic principle suggests that all the data needed to reconstruct our three-dimensional reality might be stored on a two-dimensional surface we can't perceive. Now scale that up. If our universe is the interior of a higher dimensional black hole, its accelerating expansion could simply be the stretching of that embedded hologram, like a projection on an inflating balloon. Here's where dark energy enters the picture. The holographic boundary of this cosmic black hole wouldn't be static. It would evolve, governed by the same quantum rules that dictate how information scrambles on any event horizon. As the boundary expands, the energy required to maintain the holographic code of our universe would subtly push space-time apart from the edges inward. What we perceive as dark energy might just be the computational cost of rendering reality in ever higher resolution as the black hole grows. This theory also solves an eerie coincidence. The observed density of dark energy matches the theoretical energy of a universe-sized black hole's horizon. It's as if the cosmos is whispering, "You're not looking at a feature, you're looking at the frame." Even the Big Bang fits neatly into this model. The singularity wasn't the beginning of everything, but the moment our parent black hole formed in some higher dimensional cosmos, birthing our universe as its interior. Critics raise valid concerns. If we're inside a black hole, shouldn't there be observable signatures, anisotropies in the cosmic microwave background, or strange gravitational lensing patterns? Yet some models predict these effects would be vanishingly faint, diluted across billions of light years. Others argue the theory is untestable by definition, since we'd have no way to peer beyond the holographic veil. But the idea's real power lies in its unification of physics' greatest puzzles. Dark energy, the holographic principle, and the nature of the Big Bang all might be facets of the same breathtaking truth. We're not just in the universe. The universe is in something else, and if that's the case, the missing energy isn't missing at all. It's the glow of the projector casting shadows we've mistaken for reality. Gravity might not be a fundamental force at all, but a kind of cosmic illusion, a shadow cast by the quantum entanglement of spacetime itself. That's the radical claim at the heart of emergent gravity, a theory pioneered by physicist Eric Verland that flips our understanding of the universe inside out. Forget about dark energy as some exotic substance or hidden field. Verland argues it's simply the universe's way of balancing its quantum books, an accounting error we've mistaken for physics. The foundation of this idea lies in the holographic principle, the notion that our three-dimensional reality might be encoded on a two-dimensional surface at the universe's edge. String theory first hinted at this possibility, suggesting that the information needed to describe every particle, every force, could be stored on a boundary far beyond our perception. Verland took this further, proposing that gravity, and by extension, dark energy, isn't a force in the traditional sense, but an emergent phenomenon. Think of it like temperature. You can't point to a single molecule and say, "That's heat," because heat only exists as a collective property of countless particles in motion. Similarly, gravity might emerge from the statistical dance of countless entangled quantum bits woven into spacetime's fabric. Here's where things get mind-bending. In Verland's framework, dark energy arises naturally from the universe's need to maximize entropy, its tendency toward disorder. As space expands, the quantum information associated with its horizon grows, creating a kind of thermodynamic pressure that pushes galaxies apart. No mysterious energy field required, just the universe's innate drive to spread out like gas filling a room. This elegantly sidesteps the infamous vacuum catastrophe, where quantum field theory predicts a dark energy value absurdly larger than observed. If gravity is emergent, its strength isn't tied to vacuum fluctuations but to the way information is stored and shared at cosmic scales. But how do we test something so abstract? Observational clues might lie in galaxy rotation curves. Traditional dark matter models require invisible halos to explain why stars orbit galactic cores faster than expected. Emergent gravity, however, predicts these curves naturally, without invoking unseen particles, because the entropy gradient of spacetime itself alters gravitational behavior in low acceleration environments. Some studies claim Verland's equations match certain galaxy observations better than dark matter models, though critics point to exceptions like the bullet cluster, where gravity's effects seem detached from visible matter entirely. String theory's fingerprints are all over this idea. The holographic principle grew from string theorists' work on black hole thermodynamics, and Verland's math borrows tools from this same toolkit. If emergent gravity holds up, it wouldn't just explain dark energy, it would unite quantum mechanics and general relativity through information theory, a bridge spanning physics' greatest divide. Yet the theory remains contentious. Detractors argue it's more philosophical than predictive, lacking the precision to replace dark matter or dark energy outright. Others question whether entropy-driven gravity can explain cosmic acceleration's fine-tuning or the universe's large-scale structure. But even if Verland's vision isn't the final answer, it forces us to ask a profound question. What if the forces we think we understand are just side effects of a deeper, stranger reality, one where spacetime itself is a ledger and gravity is its ink? Negative mass sounds like something ripped from a sci-fi novel, matter that doesn't just resist gravity but actively repels it. Yet buried in the equations of general relativity is a strange possibility. Particles with negative mass could exist, and if they do, they might be the invisible hand behind dark energy's cosmic push. Picture a universe where certain chunks of matter don't fall toward massive objects like stars or galaxies, they flee from them, as if gravity itself were a force to be escaped. This isn't just a mathematical curiosity. If such particles permeate space, their collective repulsion could explain why the universe's expansion is speeding up, all without invoking mysterious new forces or energy fields. The idea hinges on Einstein's own equations. In general relativity, mass and energy curve spacetime, creating what we perceive as gravity. But the math doesn't care if that mass is positive or negative, it works either way. Negative mass would warp spacetime in reverse, creating a kind of gravitational, anti-lensing effect. Instead of bending light toward it, as a galaxy does, a negative mass object would bend light away like a cosmic repeller. Now imagine this exotic substance spread thinly across the cosmos, its cumulative push counteracting the attraction of ordinary matter. Over time, as the universe expands and dilutes, this repulsive influence would dominate, gently prying galaxies apart faster and faster. Here's where it gets even weirder. Some theorists propose that negative mass particles could form a unified, dark fluid, a single, all-encompassing medium that mimics dark matter's gravitational pull in some regions and dark energy's repulsive push in others. Near galaxies, the fluid might cluster like cold dark matter, anchoring stars in their orbits. but in the vast voids between clusters, it could switch roles, exerting negative pressure and accelerating expansion. It's an elegant two-for-one solution, replacing two cosmic mysteries with a single bizarre substance. But negative mass comes with headaches. For one, it defies our most basic intuitions about cause and effect. Push a negative mass object, and instead of moving forward, it accelerates toward you, like a car that lurches backward when you hit the gas. This creates paradoxes, like objects that could theoretically self-accelerate indefinitely, violating energy conservation. There's also the issue of stability. Most negative mass models require exotic quantum fields to prevent the substance from spontaneously annihilating or collapsing into runaway energy bursts. Yet the theory persists because of its sheer audacity. It challenges us to rethink not just dark energy, but the fundamental nature of matter itself. And if negative mass is out there, hiding in the cosmic shadows, it would mean the universe is far stranger and far more inventive than we ever dared to dream. What if the universe isn't racing toward an icy, lonely end, but gearing up for rebirth? The Big Bounce theory rewrites cosmic history as an endless cycle of collapse and renewal, where dark energy isn't a one-way ticket to oblivion, but just a temporary phase in an eternal rhythm. Imagine the cosmos as a cosmic lung, inhaling gravity's pull until everything crunches down, then exhaling in a fresh Big Bang over and over. No mysterious missing energy required, just the universe breathing in and out across eons. This idea turns conventional cosmology on its head. Instead of a singular beginning followed by eternal expansion, the Big Bounce suggests our universe was born from the ashes of a previous one. Picture the final moments of that ancestral cosmos, all matter and energy compressed into a searing hot singularity. But instead of disappearing into nothingness, quantum effects kick in, a repulsive force so powerful it bounces back, triggering a new expansion. What we call dark energy might just be the tail end of that rebound, the universe stretching itself thin before gravity finally wins the tug of war and pulls everything home again. The math behind this is as beautiful as it is radical. Loop quantum gravity, a leading contender for unifying quantum mechanics and general relativity, predicts that at extreme densities, spacetime becomes granular, like a fabric woven from indivisible threads. These quantum grains resist further compression, creating a cosmic trampoline effect. No infinite singularity, no true nothingness, just an elastic rebound where the universe's energy isn't lost but recycled. Critics point to a glaring question: where's the evidence? If the universe has bounced before, shouldn't there be scars, an imprint of the previous cycle in the cosmic microwave background, or strange patterns in galaxy distribution? Some theorists argue those fingerprints might be there, just diluted over trillions of years. Others propose that each bounce resets the cosmos, wiping the slate clean like a blackboard erased between classes. Yet the Big Bounce's real appeal lies in its optimism. It trades the bleak heat death of the universe for a cosmic rhythm as old as time itself, a promise that every ending might just be a prelude. If true, dark energy isn't the universe's death knell. It's the quiet before the next great beginning. Imagine the vacuum of space not as empty nothingness, but as a chameleon, a cosmic shapeshifter that abruptly changed its nature 5 billion years ago, flipping a switch that sent the universe's expansion into overdrive. This is vacuum metamorphosis, a theory that dares to suggest dark energy isn't some exotic force or mysterious substance, but the aftermath of space itself undergoing a radical transformation. Think of it like water freezing into ice, same molecules, entirely new behavior. Only here it's the quantum vacuum, the seething, particle-filled froth underlying reality that suddenly shifted phase, rewriting the rules of cosmic expansion in the process. The timing isn't coincidental. Around 5 billion years ago, observations showed dark energy's influence began outpacing gravity's pull. traditional theories struggle to explain why this kickstart happened so late in cosmic history. But vacuum metamorphosis offers a breathtakingly simple answer. The universe hit a critical threshold. As space expanded and cooled, the vacuum's energy density crossed an invisible line, triggering a phase transition much like steam condensing into water. Before the shift, the vacuum behaved like ordinary quantum foam, its energy negligible on cosmic scales. Afterward, it became a repulsive force, its pressure flipping from neutral to negative, a cosmic repeller stretching spacetime apart faster than gravity could claw it back. The mechanics draw inspiration from something surprisingly familiar: superconductivity. When certain materials are chilled to critical temperatures, their electrons suddenly sync up, birthing resistance-free electrical flow. Similarly, the vacuum might have supercooled until its quantum fields spontaneously aligned, unlocking dark energy's latent push. This alignment wouldn't require new particles or dimensions, just a rearrangement of the same quantum ingredients we already know exist, like a deck of cards shuffling into a winning hand. Critics argue the theory is almost too elegant. If the vacuum transformed once, why not again? Shouldn't we see evidence of earlier phase transitions in the cosmic microwave background? Proponents counter that the conditions for such shifts are exquisitely precise, like a lock that only turns when the universe's temperature and density hit just the right combination. And tantalizingly, some models suggest this metamorphosis could leave subtle ripples in the distribution of galaxies, a pattern we might detect as telescopes map ever larger swaths of the cosmos. What makes this idea so compelling is its economy. Dark energy isn't an added ingredient, it's baked into the vacuum's potential, a dormant trait that awakened when the cosmos grew old enough. It transforms the universe's acceleration from a puzzle into a natural evolution, like a caterpillar becoming a butterfly. And if true, it hints at something even more profound: the vacuum isn't static. It's alive with possibility, capable of sudden, universe-altering change. The question isn't just what dark energy is, but what the vacuum might do next. The cosmological constant has always been the steady hand guiding dark energy's influence, a fixed value etched into Einstein's equations. But what if that constancy is an illusion? Quantum field theory, the bedrock of particle physics, has a trick up its sleeve: renormalization, the mathematical magic that lets infinities cancel out to reveal finite, measurable quantities. This process isn't just a technicality. It suggests that fundamental constants might not be so constant after all. Enter running lambda, the idea that the cosmological constant shifts with the energy scale of the universe, like a dial turning as the cosmos expands and cools. Picture this: in the searing heat of the early universe, particles collided with energies trillions of times higher than anything our largest accelerators can produce today. Under those extreme conditions, the vacuum itself might have thrummed with a different energy density, making the cosmological constant far stronger or weaker than the faint whisper we measure now. As the universe expanded and energies dropped, lambda could have run to its current value, like a river smoothing stones as it flows downstream. This isn't just speculation, it's grounded in how quantum fields behave. The strength of forces like electromagnetism changes depending on the energy at which you measure them. Why wouldn't the vacuum energy and thus dark energy follow the same rules? The math behind running lambda is both elegant and thorny. Renormalization group equations, the same tools physicists use to describe how interactions evolve with energy, could track lambda's journey from the Big Bang's frenzy to today's cosmic calm. Some models suggest this running might explain dark energy's curiously tiny observed value. If lambda started orders of magnitude larger but decayed as the universe cooled, its current weakness wouldn't be a mystery, just the natural outcome of cosmic aging. But there's a catch. For this to work, the running must hit a fixed point where lambda stabilizes at late times, matching our observations of accelerating expansion. Nailing down that behavior requires exotic quantum fields or symmetries beyond the standard model, like supersymmetry or extra dimensions. Without them, the theory risks predicting a lambda that either vanishes entirely or balloons uncontrollably, neither of which fits the universe we see. Critics argue that running lambda merely replaces one fine-tuning problem with another. If the cosmological constant changes, why does it land precisely where life can exist? Proponents counter that the same quantum fields driving the running could naturally settle into life-friendly values, like a ball rolling into the shallowest valley on a bumpy landscape. Others point to tantalizing clues in the cosmic microwave background, where slight anomalies in temperature fluctuations might hint at dark energy's evolving nature. What makes this theory so compelling is its refusal to take constants at face value. If lambda runs, it ties dark energy to the same quantum mechanics governing everything from electrons to black holes. A unified framework where the universe's expansion isn't dictated by some arbitrary number, but by the same dynamic rules shaping all of reality. And if that's true, the mystery of dark energy might not be a missing piece of the puzzle, but a sign we've been reading the instructions wrong all along. Black holes have long been cosmic paradoxes, regions of space so dense that not even light can escape their grip. But according to Stephen Hawking, they aren't the eternal prisons we once thought. In a groundbreaking revelation, Hawking showed that black holes slowly evaporate, leaking energy in the form of ghostly radiation. Yet this escape comes with a price. Information, the very building blocks of reality, seems to vanish forever, violating quantum mechanics' sacred law that information can never be destroyed. This is the black hole information paradox, and its unresolved tension might hold the key to dark energy's elusive nature. Imagine throwing a book into a fire. The pages burn, but in principle, every word could be reconstructed from the ashes, smoke, and heat. Information is preserved, just scrambled. But toss that same book into a black hole, and according to Hawking's original math, the information is obliterated when the hole evaporates. Poof, gone. Physicists have wrestled with this for decades, proposing wild solutions like holographic storage on the event horizon or wormholes shuttling data to other universes. But here's the twist. What if the energy carrying that lost information isn't vanishing? What if it's bleeding into the fabric of space-time itself, fueling the accelerated expansion we call dark energy? The numbers tell a tantalizing story. Black holes aren't rare oddities, they litter the cosmos, from stellar mass remnants to supermassive giants anchoring galaxies. Collectively, their Hawking radiation could represent an enormous, diffuse energy field, far too faint to detect directly but pervasive enough to nudge the universe apart. Picture trillions of invisible embers, each whispering a fraction of a lost particle's identity into the void. Over billions of years, those whispers might add up to a shout, a background hum of repulsive energy tweaking the cosmos's expansion rate. Some theorists take this further, suggesting that information loss isn't a bug but a feature. In certain quantum gravity models, the paradox resolves when information isn't truly destroyed. It's transferred to the vacuum energy of spacetime, subtly altering its properties. This informational dark energy would behave unlike conventional fields, its strength tied to the universe's history of black hole births and deaths. It's a cosmic recycling program. Matter falls in, information leaks out, and the universe's expansion speeds up as a result. Critics argue this stretches plausibility. If black hole evaporation fuels dark energy, we'd expect correlations between galaxy merger rates, which produce black holes, and local cosmic acceleration, a pattern no telescope has spotted. Others note that Hawking radiation from stellar mass holes is trillions of times weaker than the dark energy we observe, requiring absurdly fine-tuned multipliers to match. But defenders counter that supermassive black holes, or primordial ones from the Big Bang, could skew the math in unexpected ways, the most mind-bending possibility. Dark energy might not be a force at all, but the universe's way of balancing its quantum books. Every bit of information lost to a black hole could leave a tiny debt in the vacuum, an energy footprint that collectively drives expansion until the debt is paid. If true, the cosmos isn't just expanding, it's remembering, its growth a ledger of everything that ever fell into the dark. Whether this theory holds or not, it forces a profound shift in perspective. Dark energy and black holes, two of cosmology's deepest puzzles, might be threads of the same tapestry, one where gravity, quantum mechanics, and information weave together in ways we're only beginning to trace. And if Hawking radiation's secrets are indeed tied to the universe's accelerating fate, then solving the information paradox wouldn't just rescue quantum physics, it might rewrite the story of everything. String theory whispers of a universe far richer than the three dimensions we know, a realm where space curls into hidden folds too tiny to see, vibrating with secrets that could rewrite reality. Among its wildest propositions, that dark energy isn't some exotic force confined to our familiar universe, but a ghostly echo bleeding through from these higher dimensions. Imagine living on the surface of a sheet of paper, unaware that an entire library exists just millimeters above you in a direction you can't perceive. Now replace the library with rolled-up, compactified dimensions, tiny, knotted loops of space predicted by string theory, and you've got the bones of this radical idea. Here's how it might work. In string theory's framework, the universe isn't just the expansive stage of stars and galaxies we observe. It's a cosmic symphony played on 10 or 11-dimensional strings, most of those dimensions tightly wound at scales a billion times smaller than an atom. But like a sealed jar leaking fragrance, energy from these hidden dimensions could seep into our three-dimensional world, manifesting as the repulsive push we call dark energy. The math behind this is dizzying. Certain string theory models suggest that the shape of these compactified dimensions, their Calabi-Yau manifolds, could determine how much energy filters into our reality. A slight twist in their geometry might tweak dark energy's strength, like tuning a radio to catch static or a clear signal. The implications are staggering. If true, dark energy wouldn't be a standalone phenomenon, but a side effect of the universe's true multidimensional nature. It's akin to watching shadows on a cave wall and mistaking them for the objects casting them. We're measuring the shadow, not the source. This could explain why dark energy's density is so perplexingly faint. In the full higher dimensional space, its effects might be robust and natural, but by the time it dilutes into our three-dimensional slice, it's barely a whisper. Critics argue this is speculative at best. After all, we've yet to detect even a hint of extra dimensions. But string theorists counter that their fingerprints might be hiding in plain sight. If compactified dimensions are leaking energy, the cosmic microwave background could bear subtle scars, anomalies in temperature, fluctuations, or polarization patterns that defy conventional explanations. Particle colliders might one day produce debris that briefly vibrates into these hidden realms, vanishing from our detectors with a telltale missing energy signature. And then there's the elephant in the room, gravity's inexplicable weakness compared to other forces. In string theory, gravity could be spreading out into these extra dimensions. Its apparent feebleness in our world just another symptom of higher dimensional leakage. If that's the case, dark energy and gravity's puzzle might share the same solution, two cosmic riddles unraveled by a single, hidden geometry. What makes this theory so electrifying isn't just its audacity, but its unifying vision. It suggests that the universe's greatest mysteries, dark energy, quantum gravity, even the nature of spacetime itself, might not be separate knots to untie, but strands of the same rope. And if those strands lead us to dimensions beyond our perception, the missing energy isn't lost. It's just waiting in a direction we've yet to learn how to look. What if time isn't just passing, it's leaking, like sand slipping through an hourglass into some unseen chamber? Physicists have toyed with a radical idea. time itself might be decaying, its essence slowly draining into another dimension. This isn't just poetic musing, it's a hypothesis that could rewrite our understanding of dark energy, framing cosmic acceleration not as a force pushing space apart, but as time itself unraveling at the edges. Picture a universe where time isn't a steady, unbroken river, but a flickering stream losing water to underground currents. As moments slip into hidden dimensions, the very fabric of reality would respond in a startling way. Space would stretch. Why? Because in relativity, time and space are woven together in a single continuum. If time weakens, space compensates by expanding, creating the illusion of a repulsive force tugging galaxies apart. It's like watching a movie where the projector's speed slows imperceptibly. The images stretch to fill the screen, distorting the action without any visible cause. The eerie part, this decay might already be detectable. Atomic clocks, those ultra-precise timekeepers governing everything from GPS satellites to quantum experiments, could theoretically catch the drift. If time is leaking, clocks in different environments, say deep space versus Earth's gravity, might tick out of sync in ways general relativity can't explain. Some models even suggest that black holes, those cosmic drains of spacetime, could be hotspots for time's disappearance, their immense gravity accelerating the seepage like a whirlpool pulling water downward. Critics argue the idea borders on metaphysics. If time is vanishing, why don't we perceive it? The answer might lie in scale. Just as a single ant doesn't notice the slow erosion of a mountain, our daily experience of seconds and hours could be too narrow to sense the decay. The effect would emerge only over cosmic epochs, like a slow-motion avalanche invisible to anyone standing too close. Yet the theory's boldness is its strength. It transforms dark energy from a thing into a symptom, a cosmic side effect of time's quiet departure. And if true, it means the universe's expansion isn't just a chapter in its story, but a countdown to something far stranger, a future where time itself runs thin, and the very concept of now becomes fluid. The question isn't just whether clocks can catch the leak. It's whether we're ready to face a reality where time, the one constant we thought we could trust, is slipping through our fingers. What if our universe isn't the ultimate reality, but an elaborate simulation running on some unfathomable supercomputer? The simulation hypothesis, once relegated to sci-fi, has gained startling traction among physicists and philosophers, and it might hold a bizarre key to dark energy's mystery. Imagine a vast cosmic computer, its processors churning through the calculations needed to render every star, every atom, every fleeting thought in our reality. Now picture that machine straining under the weight of its own code, introducing tiny errors or shortcuts to keep the simulation running smoothly. Those shortcuts, they could look exactly like dark energy to us, glitches in the matrix masquerading as cosmic expansion. The idea gains eerie plausibility when you consider how simulations actually work. Even the best virtual worlds, video games, weather models, AI training environments eventually hit limits. To save processing power, developers use a level of detail tricks. Distant objects are rendered with lower resolution, or entire regions are approximated rather than meticulously calculated. If our universe is a simulation, dark energy might be its version of optimization, a computational buffer allowing the program to expand without crashing. The accelerating expansion, just the simulation's way of thinning out unnecessary details, like a game reducing graphics quality to handle larger maps. Some theorists take this further, suggesting dark energy could be a literal memory leak. In computer science, memory leaks occur when a program fails to release unused resources, gradually consuming more capacity until performance degrades. If space-time itself is a data structure, its accelerating growth might reflect the simulation's growing inefficiency, like a cosmic hard drive filling up with invisible junk files. Even the vacuum catastrophe, the wild mismatch between predicted and observed dark energy, fits this narrative. The true vacuum energy might be the simulation's raw processing power, while the tiny fraction we observe is all that's left after system overhead. But how would we test something so meta? Oddly, there are signatures to hunt for. All simulations have finite resolution pixelation at the smallest scales. If space-time is rendered digitally, there should be a fundamental graininess to reality, a point where zooming in further reveals nothing but blocky code. Some quantum gravity models already predict this, with Planck-length pixels woven into the fabric of space. Others propose hunting for cheats, repeated patterns in cosmic constants, or statistical anomalies in particle behavior, like a lazy programmer reusing assets. The most provocative clue might be dark energy itself. In a simulated universe, the acceleration could be a deliberate reset protocol, a way to prevent conscious observers from spreading too far and overloading the system. Think of it as cosmic lag management, expanding space to keep civilizations isolated, like players in an MGM placed on separate servers to reduce load. Of course, skeptics dismiss this as untestable metaphysics, but the simulation hypothesis forces a chilling question. If dark energy isn't a force or a substance, but a feature of our programmed reality, does that make it any less real? After all, to a character in a video game, the rules of their world are absolute, whether coded or cosmic. The theory's real power isn't in proving we're simulations, but in revealing how deeply our assumptions about reality might be distorting the search for answers. Whether a glitch, a design feature, or the universe's way of saying low memory, dark energy as a computational artifact challenges us to rethink not just physics but the very nature of existence. And if the cosmos is a simulation, the missing energy isn't lost. It's just being used to render everything else. Neutrinos are the universe's most elusive ghost particles, so lightweight and uncatchable they stream through entire planets like they're not even there. But what if these cosmic phantoms, often dismissed as inconsequential, are actually the hidden architects of dark energy? The neutrino dark energy theory flips the script, suggesting that the very particles we've struggled to detect might be shaping the fate of the cosmos in ways we never imagined. Here's the twist: the neutrinos we're familiar with, those produced in supernova, nuclear reactors, and even banana decays, are far too energetic to explain dark energy. But if an ultra-low energy variant exists, a slow neutrino barely interacting with anything, their collective behavior could rewrite the rules of cosmic expansion. Picture an ocean of these lethargic particles, each with a mass so tiny it's practically negligible. Alone, they'd be powerless, but together, their combined energy density could permeate space like an invisible fog, subtly tweaking the universe's expansion rate. The math behind this idea is both elegant and counterintuitive. Quantum field theory allows for neutrinos with energies so low they hover just above zero, particles that don't so much move as linger, their presence more like a faint stain on the fabric of spacetime than a dynamic participant. If these ultra-low-energy neutrinos fill the cosmos, their vacuum-like behavior could mimic dark energy's repulsive push. It's akin to the way a gas exerts pressure on its container, except here, the container is space itself, and the pressure comes from particles that barely qualify as matter. But how could something so feeble have such a colossal effect? The answer lies in sheer numbers. Even if each neutrino contributes an almost imperceptible amount of energy, their staggering abundance, trillions passing through your fingertip every second, could add up to a cosmic-scale influence. Unlike traditional dark energy models, which invoke mysterious fields or cosmological constants, this theory grounds the phenomenon in known physics, just stretched to its most extreme and speculative edges. Critics aren't sold, and for good reason. For one, these ultra-low-energy neutrinos would be virtually impossible to detect with current technology, making the hypothesis frustratingly untestable. There's also the issue of timing. Why would their influence only dominate now, billions of years after the Big Bang? Proponents suggest that as the universe expanded and cooled, these neutrinos' behavior could have shifted, their collective energy transitioning from negligible to dominant as space thinned out. The real allure of this idea is its audacious simplicity. It doesn't require new dimensions or undiscovered fields, just a subtle extension of the neutrino family we already know. If true, it would mean the universe's missing energy isn't missing at all. It's been right in front of us all along, streaming silently through our detectors, our planet, even our bodies, unnoticed but undeniable. And that's the ultimate cosmic irony. The answer to one of physics' greatest mysteries might be written in particles we've spent decades trying and failing to pin down. Imagine two metal plates placed so close together in a vacuum that not even light can squeeze between them. At this microscopic scale, something bizarre happens. The plates snap together with an invisible force, as if space itself is pushing them. This is the Casimir effect, a quantum quirk where the vacuum isn't empty but fizzing with fleeting particles that exert real pressure on objects. Now stretch this phenomenon across the cosmos. What if galaxies, drifting through the vastness of space, experience their own version of this quantum tug-of-war, an effect strong enough to mimic the repulsive force we call dark energy? The physics behind this idea is as elegant as it is mind-bending. In quantum mechanics, empty space is anything but quiet. Virtual particles constantly blink in and out of existence, their fleeting lives governed by Heisenberg's uncertainty principle. Normally, these particles appear and vanish in perfect symmetry, cancelling each other out, but confine them, say, between two plates, and suddenly only certain wavelengths fit. Outside the plates, particles of all wavelengths froth freely, creating a pressure imbalance that pushes the plates together. It's like being in a crowded elevator where only certain people are allowed to stand in one spot. The imbalance forces movement. Now apply this to galaxies. If space at cosmic scales behaves like a quantum vacuum and galaxy clusters act like those metal plates, the gaps between them could become quantum playgrounds. The key lies in what's not there. Just as the Casimir effect arises from restricting particle wavelengths, the voids between galaxies might suppress certain quantum fluctuations, creating an energy deficit that pulls structures apart. Instead of plates attracting, galaxies could effectively repel, not because of some mysterious dark energy, but due to the vacuum's unbalanced pressures on a colossal scale. The numbers, however, are a hurdle. The Casimir force weakens dramatically with distance. It's negligible beyond microscopic scales. To make it relevant across millions of light years, you'd need a mechanism to amplify it exponentially. Some theorists suggest hidden dimensions or exotic quantum fields could bridge this gap, acting as cosmic lenses to focus vacuum energy into a measurable effect. Others propose that the universe's large-scale structure, its web of filaments and voids, might naturally resonate with certain quantum frequencies, turning the cosmos into a giant Casimir cavity. Critics argue this stretches the Casimir effect beyond recognition. After all, quantum phenomena typically drown in noise at macroscopic scales, but supporters point to eerie parallels. The observed acceleration of the universe aligns suspiciously well with the energy density you'd expect from a cosmic-scale vacuum fluctuation. And unlike many dark energy theories, this one doesn't require inventing new particles or forces, just repurposing quantum weirdness we already know exists. There's a deeper irony here. The Casimir effect was once a laboratory curiosity, a footnote in quantum textbooks. Now it might hold clues to the fate of the cosmos. If true, the same quantum jitter that nudges tiny metal plates could be shoving galaxies apart, its invisible hands shaping the universe's expansion. That's the beauty of physics. Sometimes the smallest phenomena cast the longest shadows. Here's a mind-bending thought. What if the universe is the ultimate free lunch? The zero-energy universe theory doesn't just tweak our understanding of dark energy, it turns it upside down, suggesting that everything we see, from galaxies to gamma rays, might all balance out to nothing. At its core, this idea hinges on a cosmic ledger where the universe's positive energy, the mass of stars, the heat of quasars, the crackle of radiation, is perfectly offset by negative energy lurking in the fabric of spacetime itself. Dark energy, in this view, isn't an external force or substance. It's the universe's way of keeping its books balanced, a subtle reminder that existence might literally add up to zero. Let's break this down. Imagine the Big Bang didn't create energy out of nothing. It simply split energy into equal parts, positive and negative, matter and light. That's the positive side, the stuff we can see and measure. But gravity, according to general relativity, carries negative energy. The deeper a planet sits in a gravitational well, the more energy it takes to pull it out. On cosmic scales, these two could cancel each other perfectly, like a bank account where every deposit is matched by an equal withdrawal. Even the expansion of space itself might be part of this equation. As galaxies drift apart, the growing volume of negative gravitational energy could offset the positive energy of matter, keeping the total at zero. Dark energy, then, isn't driving the expansion. It's the result of it, a placeholder for the universe's relentless bookkeeping. There's a strange elegance to this. Quantum mechanics tells us particles can pop into existence as long as they vanish quickly enough. A tiny violation of energy conservation allowed by Heisenberg's uncertainty principle. Apply that to the cosmos, and the entire universe could be a fluctuation on an unimaginable scale, its total energy always hovering at zero. It's like a cosmic magic trick. The universe isn't something from nothing, but nothing cleverly disguised as something. But how does this explain dark energy's acceleration? Here's where it gets speculative. If the universe's expansion is a mechanism to maintain this zero balance, the rate of acceleration might be tuned to keep the books closed. As matter dilutes over time, the negative gravitational energy of spacetime would need to grow proportionally to preserve equilibrium. The result, an expanding universe that speeds up, not because of an external push, but because the math demands it. Of course, skeptics raise eyebrows. For one, defining the total energy of the universe is notoriously slippery. General relativity doesn't offer a globally conserved energy the way Newtonian physics does. There's also the question of where this negative energy resides. Is it in the curvature of spacetime, the quantum vacuum? The theory thrives on grand symmetry but stumbles on specifics. Yet its allure is undeniable. It reframes dark energy not as a puzzle to solve, but as a cosmic accountant's ink stroke, one line in a ledger we're only beginning to read. What's truly revolutionary is the implication. If the universe truly sums to zero, it needs no external cause, no creator, no multiverse, no reason to ask, why is there something rather than nothing? Because in the end, there isn't just an infinite balance sheet where every plus has its minus. It's a theory that doesn't just explain dark energy, it redefines existence itself, turning the cosmos into the ultimate debt-free venture. And if that's the case, the missing energy was never missing at all. It was just the other half of zero waiting to be recognized. The universe is dying. Not with a bang, not with a crunch, but with a slow, silent sigh as entropy drags everything toward equilibrium, a state where no energy flows, no stars burn, and no life stirs. This is heat death, the grim fate awaiting our cosmos according to the second law of thermodynamics. But hidden in this bleak prognosis lies a paradox so strange it could rewrite dark energy's role entirely. What if the accelerating expansion we observe isn't some fundamental force, but a statistical fluke, a fleeting hiccup in entropy's relentless march? Think of the universe as a cup of coffee left on the counter. Over time, the heat dissipates until the coffee reaches room temperature thermal equilibrium. but zoom in close enough and you'll spot tiny fluctuations, microscopic regions where molecules briefly clump hotter or cooler than average. Now scale that up to cosmic proportions. In an unfathomably vast and ancient universe, even the most improbable fluctuations could occur, creating temporary pockets of order amidst the chaos. Enter Boltzmann branes, the infamous thought experiment suggesting that, given enough time, random quantum jitters might spontaneously assemble a self-aware consciousness. These hypothetical observers would arise from pure chance, experiencing illusions of order before dissolving back into the void. Now apply this to dark energy. If the universe is destined for heat death, why does it look so structured right now? Why are we here to observe it? One unsettling possibility is that we're witnessing a rare low entropy bubble, a statistical anomaly where dark energy's apparent dominance is just a temporary deviation from equilibrium. Like a snowflake forming in a furnace, our accelerating universe might be a fleeting exception to entropy's rule, destined to vanish as the cosmos settles into its featureless end state. The numbers are mind-numbing. For every one of these ordered fluctuations, there could be googolplexes of lifeless, empty universes where entropy reigns unchallenged. That makes our existence and dark energy's eerily life-friendly value either a miraculous coincidence or a selection effect. After all, we can only observe a universe capable of producing observers. If most of reality is cold and dead, we'd inevitably find ourselves in one of the rare pockets where conditions allow complexity, even if those conditions are vanishingly improbable. Critics argue this explanation is too clever by half. If dark energy is just a fluctuation, why does it behave so uniformly across billions of light years? Random blips should look messier, like static on a TV screen rather than a smooth, all-pervasive force. Others counter that we might be inside an especially large fluctuation, one where the ordered region stretches far beyond our observable horizon. It's like discovering your entire neighborhood is miraculously free of rain while storms rage everywhere else, unlikely, but not impossible in an infinite cosmos. What makes this theory so haunting isn't just its implications for dark energy, but for reality itself. If Boltzmann branes are even remotely plausible, how do we know we're not one of them? Maybe the galaxies we see, the laws we measure, even our memories of yesterday are all phantom patterns in the quantum foam, destined to dissolve like smoke. Dark energy, then, wouldn't be a fundamental feature of the universe, just a glitch in its slow fade to gray. Yet there's a strange comfort in this nihilism. If our universe is a statistical miracle, it makes every moment of existence, every star, every thought, every breath infinitely more precious. The accelerating expansion might be a countdown to equilibrium, but it's also a reminder that we're here at all, defying the odds in a cosmos that shouldn't have allowed it. Whether dark energy is a fluke or a fixture, one thing's certain: the universe plays by rules we're still learning to read. And sometimes the deepest mysteries aren't in the answers, but in the questions they force us to ask. What if the universe isn't just something we observe, but something that responds to us? At the outermost edge of scientific speculation lies a theory so audacious it blurs the line between physics and philosophy. The idea that consciousness itself might shape cosmic expansion, that dark energy's mysterious push could be entangled with the act of observation. This isn't just poetic musing. It's a radical reimagining of reality where the observer isn't passive but participatory, a force as fundamental as gravity or light. The roots of this idea stretch back to quantum mechanics' strangest quirk, the observer effect. In labs, particles like electrons don't settle into definite states until measured, as if reality hesitates until someone looks. Scale this up to cosmic proportions and you get the participatory universe hypothesis, a notion that the universe's very structure, including its expansion, might hinge on conscious observation. Proponents argue that dark energy's uniformity and fine-tuning aren't accidents, but artifacts of a universe expecting to be seen. It's as if space-time itself adjusts its behavior to accommodate observers, like a stage lighting up only when an audience takes their seats. But how could something as intangible as consciousness influence something as vast as cosmic acceleration? One speculative pathway ties into quantum vacuum fluctuations. If observation collapses quantum probabilities into reality, perhaps the cumulative weight of trillions of observing minds, past, present, and future, subtly biases the vacuum's energy toward stability, nudging the universe to expand in a life-friendly way. Think of it like a cosmic feedback loop. Observers emerge because the universe expands just right, and in turn, their observation reinforces that expansion. The math, admittedly, is hazy. Critics dismiss this as metaphysical hand-waving, a facile mashup of quantum mysticism and cosmology. After all, there's no known mechanism for consciousness to interact with spacetime's geometry, no equation where neurons curve galaxies. And yet, eerie parallels linger. The anthropic principle, a staple of modern physics, notes that universal constants seem improbably fine-tuned for life. The participatory universe takes this further, suggesting the tuning isn't passive luck, but an active dialogue between cosmos and consciousness. Fringe. Undoubtedly, but history's shown that today's heresy can become tomorrow's textbook. Quantum theory itself was once mocked as spooky action at a distance. Still, the burden of proof is crushing. To take this idea seriously, we'd need evidence that observation alters cosmic-scale phenomena, a staggering leap from lab-scale quantum weirdness. Some theorists propose looking for correlations between galactic clusters and the distribution of ancient civilizations, as if pockets of early intelligence left gravitational fingerprints. Others suggest that if consciousness warps space-time, advanced AI or collective human focus might one day produce detectable anomalies. What makes this theory so electrifying isn't its plausibility, but its implications. If even fractionally true, it would mean the universe isn't just for observers, it's because of them. Dark energy wouldn't be a blind force but a mirror, reflecting back our role in the grand narrative. And that raises a haunting question. If a tree falls in a cosmos with no one to see it, does space itself expand? The answer might rewrite not just cosmology, but what it means to exist at all. From quantum foam whispering in the void to parallel universes leaking energy, from collapsing dimensions to cosmic simulations glitching, what a spectacular range of ideas we've explored. The hunt for dark energy has stretched physics to its limits, pushing scientists to imagine realities stranger than fiction. Some theories, like the cosmological constant, cling tightly to the bedrock of general relativity. Others, like phantom energy or holographic universes, take daring leaps into the unknown. And then there are those wild cards, time decaying, consciousness shaping spacetime, that blur the line between rigorous science and profound philosophy. What's truly remarkable isn't just the diversity of explanations, but how each one reveals something deeper about our quest to understand the cosmos. Whether it's Einstein's blunder resurfacing as our leading clue, or the haunting possibility that we're living in a statistical fluke in an infinite void, every theory forces us to confront how little we truly know. Dark energy isn't just a puzzle about the universe's expansion, it's a mirror reflecting the boundaries of human curiosity. So where does that leave us? Without a definitive answer, and that's exhilarating, the greatest mysteries are the ones that keep us questioning, theorizing, and marveling at the absurd beauty of it all. Maybe the solution is hiding in plain sight, waiting for a fresh perspective. Maybe it'll require a revolution in physics we can't yet imagine. Or maybe, just maybe, the real treasure is the chaos of ideas we've discovered along the way. Now it's your turn. Which of these theories blew your mind? Do you think dark energy is a quantum quirk, a higher dimensional echo, or something even wilder we haven't dreamed up yet? Drop your favorite in the comments, and if you're hungry for more cosmic mysteries, hit subscribe. The universe is far from done surprising us, and neither are we. Until next time, keep looking up and remember, the best answers often start with the boldest questions.